Hello, this is the video for April 16th. We're going to do tests of statistical significance. You can see I have my yellow shirt on. I wear my yellow shirt for weddings and funerals and for videos for my scopes class. So you're getting special treatment here. Uh, let's launch into test of statistical significance. I think it's one of the more difficult topics that we do in methodology. It, it is a model that underlies a whole branch of mathematics called statistics, which has been a big growth area and is really important. And you've probably heard the expression, such and such is not statistically significant. I hear people use that term all the time, and then I listen to them, and most people don't really understand what it means. So I'm going to try to get the meaning as it was conveyed to me by mathematicians when I was in graduate school, and I think it makes a lot of sense when you see what they mean by this expression. Here's the situation that the mathematicians are worried about. Say we want to know, is there a relationship between income and gender in the population in the United States? Important question, right? We don't have that information for all the population. So what we do is we take a representative sample. We saw that in research design. We take a representative sample, say 1,200 people. Then we get to the computer. Well, we can use SAS to do this, to divide. Males on one side, females on the other. Then we take the mean for males and the mean for females and we compare them. If the means are the same, we think that there's no reason to think that males and females have different incomes or that there's a relationship between gender and income in the population. To the extent that they're different, then we're going to come to a different conclusion. Say in our example, we have our 1,200 people. We do the mean income for men, and it's $24,100. And we do the mean income for women. It's $24,050. So $50 less than the males. Can we say out in the population there's a relationship between gender and income? Think about it. Well, we can't. And we can't, the mathematicians tell us, because when we say we have the mean for men at 24,100, that's the mean in our sample. But that's not exactly what the mean is out in the population in that parameter, because there's sampling error in this. Remember, we talked about sampling error. So you don't have in your sample exactly what's in the population. Same thing for the mean income of women. So we have to have a more vigorous test to see, are what we're seeing in the differences between men and women and their income, is it due to sampling error, or is it due to out in the population there's a difference between men and women and what they make? The tests of statistical significance are the way we handle this problem. And let me first go through the general steps that you go through, and then we're going to use a specific example. We're going to do a test of statistical significance called chi-square. When we're doing a test of statistical significance, there are many different kinds, and the proper test of statistical significance depends upon the level of measurement of your variables and how many variables you have in your analysis. So there's a whole branch of statistics with hundreds of these kinds of tests of statistical significance, but they all follow the same model. And I want to give you an idea of the model and use the example of chi-square. And if you get through that and understand that basic model, that's a good beginning to this introduction to an important part of quantitative methodology. Now, these are the steps that someone goes through if they want to do a test of statistical significance. First, you formulate the hypothesis that you're going to test with this test of statistical significance. And the mathematicians have worked it out, so there are really two hypotheses at work here. And the one we're interested in is called the null hypothesis, written H sub 0. And the null hypothesis always says, out in the population, there's no relationship between these two variables. And it's the key, because the test of statistical significance is built on the idea that we're going to gather information and we're going to assume the null hypothesis is true. And we're going to look at the data that we gather and think, would a reasonable person reject that null hypothesis that says there's no relationship between these two variables? And by a reasonable person, guess who the mathematicians mean? A mathematician. So we're going to go through the reasoning a mathematician might work. So you start out with a hypothesis to test, and you're always interested in testing the null hypothesis that says no relationship between these two variables out in the population. Okay? That's where we begin. We formulate our null hypothesis that men and women have the same incomes out in the population. That might be one. Or men and women vote the same in a presidential election, if we're looking at the relationship between vote and gender. Now, what happens after we formulate the hypothesis and we have our null hypothesis we're going to test? We have to choose the appropriate statistical test, which will depend upon the level of measurement of our variables and how many variables and the nature of the variables in this study. Now, we're going to look at something called chi-square. It's a test of statistical significance used when you have two classification variables that you put on a contingency table. And I'll show you an example of a contingency table. It's chi-square is the way we ask the question: are these two classification variables that have data at the categorical level of measurement? Are there grounds to reject a null hypothesis that says out in the population there's no relationship between the two? There are other kinds of tests of statistical significance. Maybe next class we'll talk about another one called the probability of Pearson's correlation coefficient. Pearson's correlation coefficient measures the connection between two interval level variables, and the null hypothesis says in this test, the statistical test, out in the population there's no connection between these two variables. It might be years of education and income. Are they related or not? The null hypothesis says they're not related at all. And we look at something called the probability of Pearson's correlation coefficient to make that determination. Then you can get into multivariate kinds of tests of statistical significance. The analysis of variance, used when we have a dependent variable that is interval level and an independent variable that is categorical with many different categories. And finally, there's a technique we won't look at that I'm sure people who have done more advanced statistics are familiar with, called regression analysis, where we can take one variable here and we take a whole group of variables and we test, are they related? We do tests of statistical significance to see if these variables are related, and we build a kind of multivariate model based upon this kind of regression technique. It's a powerful technique. You got to be more. You got to take more than one course in methodology to get into regression analysis. But if you go to graduate school, I'm sure you'll take methodology and you'll learn this, and you'll learn how to do it in SAS. SAS is a very sophisticated regression procedure that it uses. The manual on it's about the size of a phone book. So that's the sort of thing the Congressional Budget Office is doing when they're trying to predict what is going to be the federal deficit this year. Oh God, I don't even want to hear the calculation. We're going to borrow, I'd say, $4.5 trillion this year, going to be added to the national debt. We'd like to know more than back of envelope estimate of that. It's these regression kind of models that will be used by the Congressional Budget Office to figure that out. That's something to worry about at another time. So our second step was we choose the appropriate statistical test. Then we have to choose something called the level of significance. That is, we're going to do a computation and we're going to say, well, the null hypothesis says no relationship. Now we're going to get something and we're going to say, well, if the null hypothesis is true, what is the probability? What is the chance that I would get a test statistic this big? And if it's very remote, we're going to reject the null hypothesis. And I'm going to tell you now, there's something arbitrary to it, but in social science, we usually will reject the null hypothesis if the probability of the test statistic is 0.05 or less. That is, it's so remote that only 5 times out of 100 could the null hypothesis be true, and I'm getting the results I get when I do this computation. So let's just accept 0.05 as the level of significance that we're going to use in here. Now, I want to show how we go through these steps when we do the simplest test of statistical significance called chi-square. Chi-square is used when we have two categorical variables. And the beginning of analysis for two categorical variables is we place them on what we call a contingency table. And I've got an example of a contingency table I'm going to show you here. These data are taken from the American National Election Study, 1988. I introduced you to that when we were beginning our computer assignment number 2, in which COVID-19 rudely interrupted us. So what I'm going to give you is a contingency table where we're looking at what is the relationship between sex and how people vote. And that was Bush and Dukakis in 1988. And I got asked to set up a contingency table in which it puts sex over at the top here. There's males and females. We got their columns here. And then over here is vote. This is Bush and this is Dukakis on our contingency table here. Now, a thing to note about the contingency table, and important things are out here. They're called the marginals. They sum up rows and columns. So, for instance, out here, this is the Bush row. And these are all the people that voted for Bush. 155 people voted for Bush. That was 54% of all the 286 people on this contingency table. For Dukakis, he got 131 votes out of the 286, which was 46%. So the thing to keep in mind is that Bush got 54% of the people in our sample, and Dukakis got 46. You can look it up, but that's pretty close to what the actual figures were out in the population. Now, what we want to do is say, given this information and given a test of statistical significance called chi-square that we're going to calculate, we look at the relationship between sex and how people voted for president in 1988, and we wonder, out in the population, the null hypothesis says there's no difference between men and women and how they vote. Could we reject that null hypothesis given this information here? And the test statistic that I want to teach you about is called chi-square. And it was formulated in the 20th century by Carl Pearson, a very famous mathematician in Cambridge. And I'm going to run through the kind of steps that he went through when he figured out how to do this and how to do this calculation of chi-square. And what it begins with is we're going to do a chi-square on the relationship between sex and how people voted for Bush or Dukakis in 1988. First, we start with the first step of a test of statistical significance. Remember, formulate the hypothesis to test. The null hypothesis, as it always says, will say, out in the population, there was no connection between sex and how people voted in 1988. That's where it begins. And so how Carl Pearson begins this is he says, well, we're going to set up a contingency table without the figures that we get here. We're going to put sex, males and females, and we're going to put Bush and Dukakis here. And there are 4 cells which contain information about the people that fall in that cell. Cell 1, cell 2, cell 3, cell 4. And what Carl Pearson says, well, we also have the marginals out here. Remember, Bush got 54% of the total 286. And Dukakis got 46%, which was 131 people out of that, right? So that's where the analysis begins with Carl Pearson. Then Carl Pearson says, well, the null hypothesis says males and females vote alike. There's no relationship between sex and how people vote. And his reasoning is this, that in fact, if the null hypothesis is true, that there's no connection between how people vote and their sex, then in fact, 54% of the females should vote for Bush, and 54% of the males should vote for Bush. He should do just as well among the males and females. Does that make sense? Well, then what we should say is, if the null hypothesis is true, how many people do we expect females to fall in the cell? Well, it'd be 54% of the total number of females, 168, which is 91. That is the expected value, expected if the null hypothesis is true. And among the males, there's 118 males. If the null hypothesis is true, 54% of those males should vote for Bush. The expected value would be 64. Then we go down to Dukakis, the Dukakis row. Dukakis got 46% of everybody. The null hypothesis says he's going to do just as well among males and females. So he should get 46% of the females. There's 168 females, so 46% of the 168 is 97. That's the expected value if the null hypothesis is true. Then we go down to the males. There are 118 males here. If the null hypothesis is true, we should expect 46% of those 118 males to be Dukakis voters, and that would be 54. So think in your minds, where did we get that expected values? It answers the question expected if the null hypothesis is true, and you do the calculation in that way. Okay? Then the next step, Carl Pearson says, is we know what the expected values are if the null hypothesis is true. Now let's look at the exact observed value when we did the study. We know how many females in our study voted for Bush and how many males. So let's put the observed values. And so you see, I have a second piece of information. These are the observed values. I got this off of this SAS printout, where we see exactly what the observed values when we did the study. And so we had 73 males who were Bush voters, and there were 82 females who were Bush voters. 45 males were Dukakis voters, and 86 females were Dukakis voters. And now here's where we get into the statistical test. We're looking at the expected if the null hypothesis is true and the observed. 64 and 73. Ooh, they're different. Over here, expected if the null hypothesis is true, we'd expect 91 female Bush voters, but there were 82, and so on. And notice there's a difference between the observed and the expected in these cells. And think in your mind, if the observed and the expected in the cells are close together, what does that tell you about this null hypothesis that we're trying to test out there? I'll come at you again with that. The null hypothesis gives us an expected value. What if the observed value is exactly the same in all these cells? What does that tell you about the null hypothesis? Well, what a mathematician says, it tells you you can't reject the null hypothesis. And we don't accept the null hypothesis. The official jargon is we either reject it or we don't reject it. So if the observed and the expected are the same, we're going to say that we're not going to reject that null hypothesis. Now, as the observed and the expected deviate more and more, there gets to be a point at which a rational person says, wow, these expected and observed are so different, not because of sampling error, but it's probably being driven because out in the population, males and females vote differently. That's where the reasoning goes. And now what Carl Pearson needs is this. He needs some kind of exact mathematical formulation so it could tap into the difference between the observed and the expected and give him a decision rule as to the deviation is so large that we have to reject the null hypothesis. That's the only reason we could have this big a difference. And so what he's come up with in doing this is something called chi-square. Chi-square is a technique that is we mathematically put it together, and it takes advantage of differences between the observed and the expected. So we can come up with a decision rule. How large is that difference? Now, I have his chi-square and what he came up with. Here's the formula he came up with, chi-square. And he said, what I should do is for each cell, take the observed minus the expected, square it, divide it by the frequency expected, and then do that for the first cell, second cell, third cell, and fourth cell. This summation sign here says add them all up for each of the 4 cells. Take the observed minus the expected, square it, divide it by the observed. And I've done that for cell 1. I've taken the observed minus the expected, squared it, divided by the expected. I got a 1.27. Then cell 2, I did the same thing. Observed minus expected over expected, I came out with 0.89. Cell 3, I did the same calculation, 1.5. Cell 4, I did the same calculation. I came up with what? 1.05. Then this summation means add up all 4 cells. And so I've added up all 4 cells here, and I get 4.71. 4.71 is the chi-square for this from this table that we just did. Now, Imagine if the chi-square were 0. It would be 0 if the observed and the expected were the same in each cell. Well, they're not going to be that way. And imagine, how does chi-square get big? It gets big as the observed and the expected differ more and more. Then it gets big, right? So what happens is, as chi-square moves away from 0, it's moved to 4.71. There gets to be a point at which you think it's so remote. It's so remote that I got to reject the null hypothesis. So the decision rule becomes, how big must the chi-square be to reject the null hypothesis? And it got to be big because the observed and the expected are different. That's where our level of significance comes in. Mathematicians have calculated in a 2x2 contingency table to get a chi-square of 4.71. If the null hypothesis is true, what is the probability of that? Now, it's built into the software. SAS will spit out the probability of any chi-square that you get if the null hypothesis is true. And I looked up my SAS, pumped it out, and if you have a 2x2 contingency table with this many people, and you get a chi-square of 4.71 here, right? The p-value, meaning the probability of getting a chi-square that big or bigger, is 0.03. Remember, we're using the decision rule of 0.05. So this is more remote than 0.05. 0.05 means 5 times out of 100. 0.03 means we could only get a chi-square this big if the null hypothesis is true only 3 times out of 100, even more remote. So what we do is we reject the null hypothesis using the decision rule of 0.05 that we're going to use. And we reject the null hypothesis. We reject a null hypothesis that says there's no relationship between these two variables. So we feel confident that out in the population there probably is a relationship between these two. And we feel confident because what we would expect to get if the null hypothesis is true, we didn't get. We got something that deviated so much that the probability was at 0.03. So that's the kind of decision rule we use. And I admit there's a certain arbitrariness to the 0.05, but that's what we have to use, some kind of standard, and that's pretty remote. 0.05, using that as your decision rule, means that 5 times out of 100 you'll make a mistake, and you'll reject the null hypothesis when you shouldn't have. Well, wow. For social scientists to make a mistake 5 times out of 100, 1 time out of 20, that'd be pretty good. We could live with that. Other people can't live with that sort of thing, right? They have probabilities they have things that are much more serious than that. So, for instance, what if I have to take a medicine? Did you ever read the little pamphlet they give you about the side effects? Oh, God. What if I'm taking a medicine and it says, well, if you take this medicine for 40 times out of 100, you'll grow a third ear in the middle of your forehead. My God, I probably wouldn't take the medicine. But what if it says you grow that ear in the middle of your forehead 1 time out of 100 million? Then that's a different story. I mean, I'm willing to probably live with that risk if the benefit of the medicine is enough. So different areas use different kinds of probabilities. For instance, I remember when I took my kids in for I had all those childhood diseases. I'm old enough. I had measles and chicken pox, the childhood disease, mumps. I had that. But we have vaccines, just like we're trying to get a vaccine for this COVID-19, damn. And my kids, when they went to school, before they go to school, they got to take all these things. Uh, Polio was a big one. Polio is still, we have polio. Bill Gates has made it his lifetime commitment to try to stamp out polio. Humans have only stamped out one contagious disease that I know of, and that is smallpox. And that was a horrible killer. They've tried polio, and they've got it down to a few cases in, I think, Pakistan and Afghanistan. And Bill Gates' foundation is trying to knock that thing out, to knock out polio. But you take a naturally occurring polio. You get a vaccine. My kids took the vaccine, and before your kids sign up for that vaccine, You read, they give you some information, your doctor tells you, well, it's 1 out of several million kids that take the vaccine will get the disease. And so there's a tax that's been added into the vaccine. At least when my kids took it years ago. I don't know if they cleared this up. There was a tax that went into when people take this so that it goes to children who might contract the actual disease from taking the vaccine. That probability was wow. It was like 1 out of 10 million or something like that. It was very remote, but it's still out there. So we have to learn to deal with probabilities. And in doing tests of statistical significance, we're trying to come up with a way of dealing with probabilities to make inferences about the world. Now, that's what I want to tell you about tests of statistical significance. I don't think it's easy. The first time I saw this, I thought, what the hell is this about? I got all the books and I read books on it. And my friends who are mathematicians, I asked them things. After a while, I began to think, well, this is really brilliant of these people. They're really on the ball for devising all of these tests of statistical significance that we use to scientifically analyze data that we get from our experiments. So what you should do is go to the discussion board, and this tape is probably, well, if you're seeing it, it's up. I'll create a discussion board section on tests of statistical significance. Go to it. And next week, I'm going to talk about measures of association, statistical techniques to measure how strong is the relationship between two variables. Then on Thursday, well, I'll give a kind of summary of what we've done in the semester, and I'll hand out the take-home exam, which I'm planning to give you 1 week, unless the dean hits me on the head and tells me I can't do that. The deans are all up in the air as to what's going on here. Be sympathetic to them. This is a very unusual circumstance. So my plan is Tuesday to talk about these measures of association. Then on Thursday, give a kind of summary of the course, and then email you the take home. You'll have a week to do the take home. I hope you're doing all right. Bye.